Welcome to Biogas Basics. My name is Jürgen Kube, and this is the second part of the mini-series about the gas system of a biogas plant. Condensate is the bane of a biogas plant and can cause many problems. This presentation explains how to deal with condensate formation, how to predict its production, and how to design a gas conditioning unit. Let's dive straight in. Biogas can carry significant amounts of water vapor. When the gas cools, the water vapor condenses, and liquid water accumulates in the gas system and flows towards low points where it should be removed. The condensate rate is calculated from the mass flow of dry biogas and the water load. The water load is the mass ratio of water vapor that is added to the mass of dry gas. It is not a mass fraction, but a load that is added on top of the mass of dry biogas. It is denoted with a capital X. The water load of dry biogas is calculated with the following formula. X of T equals molar weight of water, which is 18 grams per mole over the molar weight of the dry biogas, times water vapor partial pressure over absolute pressure minus partial pressure of water. The partial pressure of water vapor is the relative humidity, phi, times the saturation vapor pressure of water, Psat. The saturation vapor pressure of water is calculated with the Antoine equation, as explained in the previous presentation. For the design of condensate removal systems, the maximum possible condensate rate should be used. The correlation between water load and temperature is exponential. Most condensate will be produced by cooling the biogas the first couple of degrees. Therefore, the difference in condensate production when cooling biogas from 55 degrees Celsius to 15 degrees Celsius versus cooling it to 5 degrees Celsius is marginal. We might as well design the condensate system for complete drying. Let's do an example. A flow of 1000 norm cubic meters per hour. Biogas with a methane content of 55% flows from a digester that operates at 45 degrees Celsius. The relative pressure is 5 millibars gauge, the ambient pressure is 1 atmosphere, the absolute pressure of the gas is 1.018 bars. The digester has a gas dome which can be subjected to sunshine and the gas heats up by another 10 degrees Celsius. First, we calculate the density of the dry biogas at reference conditions to get to the mass flow of dry biogas. We use the ideal gas law. The density is the pressure times average molar mass over gas constant and temperature. Here, 1.26 kilograms per norm cubic meter. The mass flow of dry biogas is 1.26 tons per hour. Next, we calculate the saturation vapor pressure of water with the Antoine equation. It is 0.156 bar. We can use Raoult's law to calculate the volume fraction of water vapor in the biogas. It is 0.156 over 1.018 bar, or 15.3%. That means 15.3% of the volume is filled with water vapor. Now we calculate the water load. It is 0.114 kilograms per kilogram. Per ton of dry biogas, 114 kilograms of water vapor are transported. In our example, the mass flow of dry biogas is 1.26 tons per hour and the water vapor flow on top of that is 146 kilograms per hour. The condensate system should be designed for this value. When biogas flows from the biogas plant to the gas consumers, it must undergo a conditioning step. This step comprises a drying and a compression step, often also a desulfurization step, but I will ignore that here and make a designated presentation about desulfurization in the future. I want to discuss the order of compression and drying. Biogas can be compressed first and then cooled and dried, or cooled and dried first and then being compressed. In the first option, warm and humid biogas comes from the digesters and is compressed first. The biogas will carry some condensate and can also contain water droplets entrained in the flow. The humid flow is compressed and heats up in the blower. The compressed gas is then cooled in the first heat exchanger against ambient temperature via a table cooler. In a second heat exchanger, the gas is cooled against a brine provided by a refrigerant chiller system. A two-stage gas cooling system is state-of-the-art in biogas plants and provides energy savings compared to a single-stage refrigerant cooling system. More condensate is removed after the second heat exchanger. The produced biogas is saturated but at a low temperature. Nevertheless, it can still form condensate in downstream pipelines if the ambient temperature is below the brine temperature. The advantages of this arrangement are that the pressure in the suction pipe stays positive, and the heat exchangers can be designed a bit smaller, and their pressure drop can be overcome with the blower. The disadvantages are that the blower must be designed for the humid volume flow. Entrained droplets can damage the blower. The generated outgoing biogas stream is still saturated, albeit at low temperature, but still can produce condensate. Lastly, This layout requires 2 condensate outlets plus a third further down the line. A biogas heater might be required downstream of the last heat exchanger to prevent condensation in the pipeline to the gas consumers. The alternative arrangement has the 2 heat exchangers first and then compresses the gas to the target pressure. Condensate is removed after the second heat exchanger. The temperature increase in the blower leads to a partially saturated biogas outlet stream that will not form condensate if the gas pipe is insulated and not too long. This is the main advantage of this configuration. Other advantages are that the blower is protected from water droplets, after the second heat exchanger is typically a demister, and that the blower must only transport the dried biogas flow. The major disadvantage is that the pressure at the inlet of the blower will become negative in most cases. The heat exchangers have a large pressure drop of around 10 to 20 millibars. If the pipeline develops a leak, air can be sucked into the biogas, which in theory can create an explosive atmosphere. In reality, this is very unlikely, though not impossible, as the volumetric ratio of air to biogas must be somewhere between 3.5 to 1 and 11 to 1 for a flammable mixture. So, there must be far more air than biogas for a flammable mixture. However, small local zones will form around a leak that contain just the right gas mixture for an explosion. Another disadvantage is that the condensate must be withdrawn under vacuum, which requires a local pump. Personally, I prefer the latter configuration. Oxygen ingress can be detected with an O2 sensor that stops the blower if oxygen starts to accumulate in the gas from the blower. I also recommend using a duty standby or duty-duty standby arrangement of blowers. A single blower is a single point of failure. Blowers are also often undersized because of unexpected high pressure drops in biogas pipes, or because the water vapor load is forgotten in the design phase. Chillers are another critical point in the gas conditioning unit, as they fail frequently and benefit from a duty standby arrangement. The location of the gas conditioning unit is also important. This figure shows the biogas plant and then a long pipeline with humid gas to the gas conditioning unit. This configuration is often preferred by the original equipment manufacturer of the gas consumer equipment. The OEM wants to supply the gas conditioning to control the quality of the gas at the inlet of the gas consumer and to reduce costs. The gas conditioning is moved next to the gas consumer. However, this configuration is not recommended. Generally, humid gas pipes should be as short as possible. They have a higher pressure drop because of the higher volume flow and the condensate dropping out in the pipe. The pressure drop on the suction side is also more critical, as it contributes to the vacuum on the suction side of the blowers. Long humid gas pipes can also lead to the formation of ammonium bicarbonate crystals in the gas pipe. These crystals are formed in ammonia-rich biogas where temporary condensation occurs. They create a fine white dust which can be identified by the typical ammonia smell. The dust can damage gas consumers if they do not contain police filters. Generally, the gas conditioning unit should be moved as close as possible to the biogas plant to minimize the length of humid gas pipes. Once the gas has been dried and pressurized, it can flow with higher velocities in smaller pipelines, and the pressure drop is less critical as it can be overcome with a slightly larger blower. This slide shows all formulae required to calculate the condensate production and the gas conditioning steps. The enthalpy of the humid biogas stream is the mass flow of the dry biogas times the sensible heat term of the dry biogas, Cp times T minus reference temperature plus water load, times sensible heat term, Cp delta T plus the latent heat term heat of evaporation. The reference temperature is set to 0 degrees Celsius to simplify the formula. It does not have to be identical to the temperature of the reference state. We can calculate the cooling demand of a heat exchanger with the first law of thermodynamics for open systems. The cooling demand is the difference of the in- and outgoing enthalpy streams. The blower is considered to be adiabatic. It loses so little heat over its surface that the heat term can be ignored, and the power demand of the blower is the enthalpy difference of the in- and outgoing streams. During compression, the water load changes, but the volume fraction of water, denoted with a small x, stays the same. The heat capacity of an ideal gas in kilojoules per kilogram and Kelvin can be calculated from the heat capacity ratio kappa and the molar mass of the respective gas. For biogas, kappa is roughly 1.3. The water vapor load is molar mass of water over average molar mass of biogas times water partial pressure over absolute pressure minus partial pressure of water. The molar or volume fraction of water in humid biogas is partial pressure of water over absolute pressure, which is relative humidity times saturation vapor pressure over absolute pressure. And the outlet temperature of a blower using ideal gas is inlet absolute temperature times adiabatic efficiency of the blower, -1 plus outlet to inlet pressure to the power of kappa, -1 over kappa, over blower efficiency. Let's do an example. A biogas stream of 1000 norm cubic meters per hour, 55% methane, 55 degrees Celsius, 5 millibar relative pressure is first cooled and then compressed. The first cooling step using a table cooler cools the gas down to 40 degrees Celsius. The pressure drop over the first heat exchanger is 10 millibar. The second heat exchanger using a refrigerant chiller cools the gas to 4 degrees Celsius. The pressure drop is 10 millibar again. The blower increases the pressure by 200 millibar. What is the cooling demand of the table cooler and refrigerant cooler, and what is the temperature and relative humidity of the biogas after the compression? The table shows the result. The first heat exchanger reduces the enthalpy stream of the biogas from 125.7 to 60.2 kilowatts. It requires 65.5 kilowatts cooling. The refrigerant chiller cools the biogas by 54.4 kilowatts. The condensate production is 139.9 kilograms per hour, almost all of the water vapor content of the incoming biogas. In the next step, the biogas is compressed in the blower. The water vapor volume content of the biogas stays constant in the compression step. This must be considered when calculating the enthalpy of the outgoing stream. The power demand of the blower is 11 kilowatts. The temperature of the biogas after the compression step is 33.8 degrees Celsius. Its relative humidity is 17.3%. Here we can see the importance of the table cooler. A table cooler uses 3 to 5% of the cooling duty in electricity, a refrigerant chiller around 20%. In our example, the energy savings are around 10 kilowatts, equivalent to 15,000 to 20,000 pounds per year at the time this presentation was made. If the gas pipes are longer, the compressibility of the gas must be considered, and the flow is no longer isothermal. The impulse and heat balance must be solved with this ODE system, which can be integrated with explicit Euler or Runge-Kutta. The heat loss term is -4 times heat transfer, coefficient U over density, and inner diameter times local temperature minus T infinity. The formula for the heat transfer coefficient U depends on whether the pipe is above ground or buried. For the buried pipe, it depends on the heat conductivity of the soil and the depth of the pipe. T infinity is the soil temperature, which is the average ambient temperature. For the above ground pipe, it depends on the heat transfer coefficient on the inside and outside of the pipe and the heat conductivity of the pipe material. T infinity is the ambient temperature, which can vary over the day and season. This heat balance is for a non-condensing gas. The formula should be used for long gas pipes, for example in microgas nets with decentralized gas consumers. Here is the index. Stop the presentation if necessary. We continue with the previous example. The flow from the blower has a temperature of 34 degrees Celsius and a dew point of 4 degrees Celsius. It flows through a 300 meter long DN200 pipe with a roughness of 0.1 millimeter. The pipe is buried in a depth of 1 meter. The soil has a heat conductivity of 3 watts per meter in Kelvin. The blue line shows the pipe pressure. At the end of the pipe, the pressure has dropped to 172 millibar. The orange line is the gas temperature. It approaches the soil temperature, which is the dashed line, and is almost 10 degrees Celsius at the end of the pipe. The chilling step to 4 degrees Celsius ensures that the gas will never start to condense as the dew point is below the soil temperature. Condensate will not only form in biogas pipes that are in continuous use, but also in pipes that are only used temporarily. These lines are biogas pipes to the flare and reject pipelines that recycle biomethane and sometimes CO2 back into the gas storage of the AD plant. Under normal operation, the flow in flare and reject lines is 0. But water vapor can diffuse into the pipe and condense there, creating a permanent concentration gradient that drives diffusive transport. These gas lines will slowly flood over time and require condensate removal. Flare and reject lines should tap into a gas pipe from above to minimize condensate formation, but some condensate will still form in the section behind the high point. Reject lines can be purged with a small biomethane bleed stream, for example a sample gas stream. The stream will be in the region of several liters per hour. The biomethane is dry, and its convective transport negates the diffusive ingress of water vapor. Gas pipes can be placed below or above ground, but variants have advantages and disadvantages. Below ground pipelines can be made from high-density polyethylene or HDPE. HDPE is a cheap material, especially when the pipe comprises mainly long straight runs. it shouldn't be used above ground as it can become brittle from UV exposure. Above ground pipework should be made from stainless steel, typically 316, or other corrosion-resistant steels. Above ground pipework requires structural reinforcement and must be laid on gantries to avoid sagging, which contributes to the cost of the pipeline. Biogas pipes create condensate, and the condensate must be removed at every low point. The pipes require a slope. 1% if the biogas flows in the direction of the condensate, and at least 3% if it runs against the biogas flow direction. 3% doesn't sound like much, but if the pipe is 100 meters long, the height difference is 3 meters, so avoid countercurrent flow of condensate. If the gas pipe is buried below ground, condensate must be removed via condensate shafts, which are a major hazard. CO2 can diffuse through the water much faster than CH4 and can accumulate in the shaft. Because it is heavier than air, it will stay there and can lead to asphyxiation if a person enters the shaft. The slope of a pipe can be easier controlled in above-ground pipes on gantries, and condensate can be safely withdrawn via condensate pots. Buried gas pipes can sink if vehicles are moved over the pipes or the ground has not been compacted prior to laying down the gas pipes. If a pipe sags, it will create a local low point with no condensate removal. I would avoid buried pipes if the gas is still humid and only go below ground if the gas has been chilled below soil temperature, so that no condensate can drop out. Generally, biogas pipes do not require insulation. The only exception is the line downstream of the gas compression, if the aim is to keep the gas partially saturated. Let's summarize. Biogas is water vapor saturated, and condensate will drop out in gas pipes as the gas cools. The maximal condensate production can be calculated from the water load of the gas. Generally, try to keep humid gas lines as short as possible and above ground. Do not bury them. The gas conditioning unit dries and compresses the biogas. The order of the drying and compression steps is important. The order can be compression cooling or cooling compression. Both arrangements can be relevant. The cooling compression configuration requires lower capex and opex, but creates a vacuum on the suction side of the blower, which can be a safety issue in theoretical cases. For long gas pipes, the impulse and heat balance must be solved simultaneously by integrating an ODE system along the pipeline. Every low point in the gas system will eventually flood with condensate if it does not have a condensate removal point. That is also true for flare and reject lines that are not in constant utilization, but can still accumulate condensate over time as water vapor diffuses into the pipe and condenses there. Ensure that gas pipes have the right slope and that condensate flows preferably in the direction of the biogas flow. This concludes the presentation about condensate formation. Condensate formation is straightforward, and the consequences of condensate dropout are so obvious that they are rarely taught. Yet many biogas plants have problems with their condensate systems, so I decided to dedicate a part of this mini-series to it. I hope you have learned something new, and I'll see you in the next presentation of Biogas Basics.